Welcome to hear the first lecture on air quality, and this is the introduction. During this lesson, I will try to answer the questions on what is air quality and what are the sources that weaken the air quality. I will tell you a little bit about the road traffic emissions and WHO guidelines for air quality. So, let's get started. What is air quality? It is basically the quality of the air that you breathe. Air pollution can happen for many different reasons, and in the pollution process, the natural state of the atmosphere is changed. Polluted air is associated with health effects like increased mortality from strokes, heart disease, and acute respiratory infections, to mention few. Air quality can be weakened by pollutants from several sources, like motor vehicles, ships, aeroplanes, road traffic, and industrial facilities, forest fires, and stoves in the home. Different kinds of emission sources have their own characteristics in pollution compounds. It also depends on locations. Which sources of pollution are the most significant one at the site? It is very common that the road traffic has a significant effect on air quality in urban surroundings. Since the emissions of road traffic are released close from the breathing level. The most significant components from the road traffic exhaust gases are nitrogen oxides and fine particulate matter, if we consider only health and air quality. Both these compounds have many different kinds of health effects, and for example, long-term exposure to them may cause asthma and reduce lung functioning. There is no safe limit for particulate matter concentrations, below which there are no health effects at all. WHO has given guidelines for air quality. Air pollution is an environmental risk to health, and by reducing the air pollution levels, countries can reduce the burden of many health effects significantly. The idea behind the air quality guideline values are that they should not be exceeded there where people live and stay. Particulate matter can contain different elements and compounds like sulfate, nitrates, ammonia, black carbon, and so on. And in general, fine particulate matter is defined to have a diameter of 2.5 microns or less, and it's called PM2.5. And while breathing, it can penetrate deep into the lungs, and some can even enter the blood system. In long-term exposure, they have many health effects. Guideline values for PM2.5 is 10 micrograms per cubic meter in annual level. The highest daily value shouldn't exceed 25 micrograms per cubic meter. WHO guidelines for nitrogen oxides or nitrogen dioxide is 40 micrograms per cubic meter in annual level, and the highest 1 hour mean shouldn't exceed 200 micrograms per cubic meter. Nitrogen dioxide is a quite typical pollutant of anthropogenic combustion process. and by that I mean heating, power generation and engines in vehicles and ships. So thank you for listening to the first part of the lectures on air quality. See you during the next class. Welcome to hear the second lecture on air quality. This time we are going to discuss about road traffic emission calculations. During this lecture I will show you some basic ideas behind the estimating the nitrogen oxide and particulate matter emissions caused by road traffic. I will present the calculation method and what kind of data we need to get started with the emission calculations. In the end of the lecture, I will show you a couple of examples. The European Environmental Agency has published an emission inventory guidebook, and it includes a chapter called Exhaust Emissions from Road Transport, and that is also our backbone here. The guidebook describes 3 different types of methods to calculate the emissions: tier 1, 2 and 3. Which ones should we choose then? The answer depends on the available input data. While tier 3 method needs the most accurate information, tier 1 is a rough estimate with less information from the road and the country. In Finland, we usually choose the tier 3 method since we have quite much data available, and luckily it's openly available as well. The emission parameters in the tier 3 method depends on 4 things: the type of vehicle, so that means is it a passenger car, light commercial vehicle, bus, trucks without a trailer or with a trailer, and the fuel type the vehicles use, that means the petrol, diesel, gas and so on, and on the environmental class of the vehicles. I mean by environmental class the Euro class, and the driving speed of the vehicles. I've sketched the emission calculation method in 4 steps. The step 1, we first collect the emission parameters from the EEA EMEP guidebook, and this is done for every vehicle category and subcategories on fuel type and on Euro class, and for every driving velocity necessary, since the emission parameters depend on all these 4 things. In step 2, we look the performances of each subcategory type in fuel and Euro classes and how they are distributed, and combine this information of performance with the emission parameters. In step 3, we look how much there are vehicles in each category in each road segment we want to study, and combine this information to the emission parameters and performance information from step 2. The information is combined together in step 1, 2 and 3. Basically it's just mathematics with multiplications and additions, and then we get the emission factors in grams per kilometer per day. The total emissions are then multiplied with the length of each road segment to get and then we get the emissions in units grams per day or tons per year. So here is one more slide on the input data we need in the 3 method. Vehicle category information in car fleet composition by vehicle categories, So passenger car, light commercial vehicles, buses, trucks without a trailer and trucks without a trailer. These are main categories, and in all of these main categories we have subcategories for fuel type and Euro class. In Finland, this information can be found in Lipasto. That's a database of Technical Research Centre of Finland. And then we need information from the road and each road segment we want to study. That means the speed limits and number of different type of vehicles on the road. And this information is also publicly available on these websites. This is one simple example of the emission calculations. One application of emission calculation studies would be to find out how much emissions one transport event causes. A truck with a trailer that uses diesel fuel and that engine is classified in Euro 4 class travels from St. Petersburg to Helsinki. So travel speed in average is 80 kilometers per hour in average in that section. Emission parameters for NOx is 6.1 grams per kilometer and the driving distance is approximately 320 kilometers. So then one transport causes almost 2,000 grams of NOx. However, if the truck was classified as Euro 6 class, the emission parameter of NOx would be then only 0.3 grams per kilometer. That's quite a lot less than for Euro 4 class engine. Then the transport event from St. Petersburg to Helsinki would cause only 93 grams of nitrogen oxide. In the project GreenInterTraffic we did exercise where we want to calculate the emissions from Helsinki to St. Petersburg on the road E18. The input data is from the year 2018 and that means that we have the data of traffic fleet composition, traffic speed, number of different type of vehicles on the road from the year 2018. And in this picture you can see the number of vehicles per day in average on the road. The darker the color on the map on the road means the more vehicles on the road there are. And then we calculated the NOx emissions that caused by the road traffic for the road E18 from Helsinki to St. Petersburg. The calculations are done separately for small road segments, and we take this into account that the traffic composition varies on these segments. And we calculated also the particulate matter emissions caused by the road traffic on the road E18. The darker the color, the more emissions there are, and you can see the scales on the left side of the picture. So conclusions on the emission calculations. Now that the emission calculation methods are known, different kind of emissions can be made. Emission calculations can be made. For example, emission calculations of one single trip, and that would be probably quite interesting for transport companies. And the emission inventories for whole network to find out how much pollutants are emitted per year, or emission dispersion modeling based on the calculated emissions of the road to find out the concentrations of each pollutant in ambient air. And point 4 would be to calculate different kind of future scenarios and impact of the different emission reduction actions on total emissions. By changing the suppositions behind the calculations, like changing Euroclass distribution or share of different type of vehicles on the road, or even alternative road alignments, different type of scenarios can be tested and seen example what kind of impact these have on environment. Points 2, 3 and 4, I think they would be quite interesting for emission inventories, and to the air quality dispersion modeling results would be interesting for the authorities and for city planning purposes. So thank you for listening to the second part of the lecture. See you in the third one then quite soon. Welcome to hear a lecture on air quality. This time we are going to discuss about how to estimate the impact of the emission caused by the road traffic. This is the third part in the lecture series on air quality, and my name is EmmiLaukkanen. So this video lecture will present you how to estimate the air quality impact of the road traffic emissions. The lecture explains the basic principles of the air quality dispersion modeling, and in the end of the lecture I will show you the results of the dispersion modeling exercise done for the road E18. Emission dispersion model is a tool to make assessments on the impact of the emissions. The dispersion model tells how the emissions disperse and dilute into the ambient air around the emission source. For different kind of emission sources, there are different kind of dispersion models. For road traffic, we use a model that treats the road traffic emissions as line sources, and it is called CAR FMI. It is a model developed by the researchers of Finnish Meteorological Institute, and it has been verified in several articles and dissertations. By the way, the CAR FMI is an acronym from the words contaminants in the air from a road. Basically, the model needs as accurate information of the emission source as possible. For road traffic, we need the information on travel speed, traffic composition, and Euroclass distribution and fuel type distribution to make emission calculations. We also need the emission parameters from the European Environmental Agency Emission Inventory Guidebook. Then we need information of the prevailing conditions, that is, the weather observations and background concentration observations from the area we want to study. The modeler forms from the input data, time series, and spatial data with coordinates for the dispersion model. Then the model is run, and the model calculates the atmospheric chemistry, and in dilution and dispersion it takes the effects of the terrain and meteorological conditions through the meteorological observations time series into account. The calculations are done for every calculation point in the research area. As a result from the dispersion model, we get an hourly time series of concentrations in each calculation point. With the statistical analysis, we can get regional concentration maps that are comparable to air quality guideline and limit values. After this, we can make decisions on land use or maybe compare different kind of planning alternatives and so on. Every time when it's possible, it is advisable to compare the model concentrations, the measured air quality observations, to verify the results. This slide is just to remind us about the WHO guideline value for the annual concentrations for fine particulate matter and nitrogen dioxide. Guideline value for PM2.5 is 10 micrograms per cubic meter in annual level. The guideline value for NO2 is 40 micrograms per cubic meter in annual level. This exercise is a continuation to the exercise I showed you in the previous episode of this lecture series in emission calculations. In the exercise, we calculated the emissions caused by the road traffic for the road E18 from Helsinki to St. Petersburg. Now we also calculate the concentrations only on road A18. It is noteworthy that the concentrations dilute quite fast when the distance grows from the road. Now I just wanted to show what would be the maximum concentrations on the roadside. From this picture we can see that the concentrations are clearly below the WHO guideline value, 40 micrograms per cubic meter in Finland and in Russian part of the road until Viborg. The amount of heavy-duty vehicles and their low Euro classes are the reason why the emissions and concentrations on the road E18 between Viborg and St. Petersburg are higher and close to exceed the WHO guideline value. The guideline value is exceeded only in small part of the road. The previous slide was about nitrogen dioxide and this one is for fine particulate matter PM2.5. The concentrations are clearly below the WHO guideline value in Finland and in Russian part of the road until Viborg. The high amount of heavy-duty vehicles and their low Euro class distribution are the reason why the emissions and concentrations on the road E18 between Viborg and St. Petersburg are higher and even close to exceed the WHO guideline value. However, the guideline value is exceeded only in the small part of the road. Thank you for listening to the third part of this lecture series. If you have any questions, please send me an email. Welcome to hear a lecture on air quality. This time we are going to discuss about air quality monitoring. This is the fourth part of the lecture series and my name is EmmiLaukkanen. So this lecture will be about how to estimate the air quality based on measurements and what kind of measurements there are, and I will tell you shortly about the air quality index as well. Air quality monitoring in EU countries must meet the EU directives. Basic principle is that for each component there are a reference method to monitor it. If other methods are used, the equivalence to the reference method has to be shown. Typically, the online monitoring stations are equipped with reference method devices and equivalent method devices. The reference method or equivalent methods measurements have a daily control, regular service, and calibrations according to the measurement network's quality systems and EU requirements. The reference method and equivalent method can be applied in air quality limit value controls. In Finland, Finnish Meteorological Institute is responsible for the background air quality measurements, and the municipalities must control their own air quality according to the EU requirements. The quality of the measurements done in this way is very high, and so are the costs also. It's quite expensive. In some cases, indicative measurements or sensor measurements can be applied, but one has to accept that the quality of the data is not clearly in the same level as in reference or equivalent methods. Usually the sensors are less expensive than the high-end products, and their maintenance costs are also less. However, as told, sensor measurements can be treated only as indicative measurements. So about sensor monitoring. Low-cost sensors are a promising technology with a rapid evolution in the market, and the performance of the sensors is improving constantly. However, it is very unlikely that the sensors can replace totally the traditionally high-quality reference methods measurements in any near future. What data quality can we expect from the sensors? Well, first of all, it is recommended to have long field comparisons for sensors and reference or equivalent methods side by side. So then we see how the data from sensors behave in compared to the reference or equivalent methods. It is also necessary to evaluate the performance under different environmental conditions so that the comparison time is long enough. The high variability in performance from one sensor to another sensor is sometimes true, but this can be also tested in the field comparison, and it has to be checked before installing them to the field. The testing phase should be done in real-world conditions. It is necessary to evaluate the performance in the field and not only in laboratories. The performance of the sensor units depend on the environment. It also depends on how far they are from the emission source and on the meteorological conditions as well, and on the concentration levels. Some of the devices have very high detection limits. Post-processing the data can reduce interference with temperature and relative humidity, and it can improve the sensor performance. In the project GreenInterTraffic, we have installed 4 sensors along the road E18 on road weather monitoring sites. 2 of the sensors are located near the border area in Finland and 2 of them in Russia. The sensors measure particles in 2 sizes, PM2.5 and PM10, or that is the particles with diameter equal or less than 10 microns. And the and they measure 4 gases: sulfur dioxide, nitrogen dioxide, ozone and carbon monoxide. The sensors were first compared to reference and equivalent methods in Helsinki Kumpula for a couple of months during the summertime 2019. And then the installation of the sensors were done in Russia in September 2019 and in Finland December 2019. The data is available on the web page of the project, and it is still in raw format and it has not been post-processed. It should be evaluated as an estimation only. The measurements continue until the end of this year, 2020, and then there will be again a comparison in Helsinki. We will compare the sensor measurements against the preference and equivalent methods. And in this map you can see some light colors where the AQT sensors are installed. And the color of the sensor signs are coded according to the air quality index. And you can read more about the index also on the web page, and I will tell you something during the next slides. So, air quality index is used to describe the air quality in simple terms, and it should be easy to understand in color scale. It is based on measured air quality data, and it gives an overall characterization of the actual air quality. So green one means that the air quality is good, yellow one it is satisfactory, orange fair, red poor, and purple very poor. And in this table there are also mentioned health impacts and other long-term impacts. But how we get these colors is we need the sub-index for each measured component, and the highest sub-index determines the overall air quality index at the station. For more information, you can see our webpage of FMI and the project webpage. There is this question mark, you can see more information there. So thank you. This one was the last one of this video lectures on air quality. If you have any questions, throw me an email and I'll get back to you. Bye.